Hello everyone, welcome to the course on mathematics for machine learning. Today we will be learning about system of linear equations and their geometry. So we won't be solving system of linear equations. We will just learn about our system of linear equations and their geometrical interpretations, and we will see in how many ways we can think of a system of linear equation and their solutions. And later on, after few lectures, we will be actually solving them. So today is just the intro of the problem statement and different point of views on that. So let's start with the notations. So I will be using scalars with lowercase such as a, b, c, alpha, beta, gamma. Then vectors, we will be throughout the lecture series, we will be following the same notation actually. So vectors will be represented with lowercase, say x, y, z. Matrices will be represented in uppercase, say a, b, c. Then x transpose A transpose is a transpose of a vector or matrix. A inverse of a matrix. Don't worry if you don't know about the transpose or inverse, we'll discuss about it. And if x and y are two vectors, then their inner product will be shown like this, their dot product will be shown like this. So these are some basic notation and we will stick to them for the entire course. As we move ahead, I will share the notations whatever we require in every lecture. So let's begin. So what is linear algebra? So we'll start with the formal definitions and we'll dig deeper into it. So linear algebra is the study of vectors and certain rules to modify them. Yeah, that looks cool. Okay, so study of vectors and we apply some operations on that, some rules on that to modify them. Maybe we can scale them or we can add two vectors, get another vector, something like that. So actually, what is a vector? So you can consider, again, let's start with the formal definition. So vectors are special objects that can be added together and multiplied by scalars to produce another object of similar kind. So these are actually two properties. So once you if you add two objects, the resulting object should be of similar kind, and when you scale an object, then also resulting object should be of similar kind. So an object that satisfies these two properties can be considered as a vector. So in machine learning point of view, vectors are nothing but, you can say, elements of Rn, tuple of n real numbers, which are vectors. Mostly we will be considering in our entire course a definition of vector as this. However, there are different point of view, like physics point of view, computer science point of view, mathematics point of view. But for our machine learning approaches, we will be considering a vector as element of Rn, a tuple of n real numbers. So for example, if you consider 2D plane, so this R2 is nothing but a 2D plane representation. Similarly, if you want to represent a three-dimensional space, then you have to write R3, something like that. So R2 is a two-dimensional plane, and so this vector is in that plane. So if this symbol is belongs to, that means x, that is 1 and 2, that belongs to the plane R2. So you can say, or in other words, x is an element of R2. So this is just some notation, those who don't know, however most of you might be knowing it. So let's check the property of this vector. So if we take two vectors from an R2 two-dimensional plane, and if we add them, and it is quite intuitive that if you take two vectors from R2, if you add them, the resulting vector definitely has to be in R2. So yeah, that's quite intuitive. And again, if you take a vector and multiply by it by a scalar, then obviously it will scale the vector, but ultimately the result will also be a vector in the same R2 plane. Something like, if this is x, then lambda times of x will be, if lambda is greater than 1, then it will be something like this. So again, it is in R2 plane and it is a vector. So basically two fundamental properties are satisfied here. So for our case, a vector will look something like this. Here it would be Rn most of the time. And if you see machine learning, almost all front end thing, the feature representation we say, they are all vectors of in some dimension, say Rn. So I guess now we are clear with the vector. Now let's take a look at the system of linear equations. So this solving the system of linear equation is the central problem of linear algebra. So the following content that I will be discussing in for next 3 to 4 minutes is taken from MIT OCW 1806 linear algebra lecture by Gilbert Strang. So I have attached the link of that video in the description. You can go and take a look. Take a look. But however, I have whatever important things are there, I have tried to put it here. So there is no need to do that. But still, if you want to explore, you can do that. So, and probably linear algebra series by Gilbert Strang is the, I would say, is the best content on internet to learn linear algebra. Even I have started from there. It's 3-4 years back. So now we will take a very simple thing. Again, we are not trying to propose some set of steps to solve linear equation or something like that. We are just trying to look at the problem, how to interpret the problem. That's the goal of this lecture. So we will be looking at a simple case, n linear equation and n unknowns. So we have a row picture, basically three kind of viewpoint we will be having. So first will be a row picture. In that case, we will consider one equation at a time, like visualizing one equation at a time. There is something like a column picture, that is the most important one for us, and something like matrix form, that is a general linear algebraic way to solve. So let's start with the row picture. So let's take a very simple example. Two unknown, two equations. So suppose these are the two unknowns x1 and x2, and these are the two equations. And also you can write this thing in matrix form. So you can write something like ax equal to b, where a is this coefficient matrix, x is this, and b is this. So let's look at the row picture. So if you consider each equation, each row of this matrix as a line in a 2D plane, then a graph will look something like this. So this blue line shows the row 1, this is this row, and the green line shows the row 2. This row is shown here. So the solution of these two equations is nothing but a point where x1 and x2 which satisfy both the equations. So obviously it will be the intersection of these two lines, which is this point. So this point is nothing but the solution of the equation. So you can see in row picture, you just have to consider each equation as a line in 2D plane in this case, and draw it, and whatever is the intersection point, that is the result of that is a solution for your system of linear equation. So as simple as that. So this is the row picture, and let's look at the column picture. Again, you can see these equations can be represented in this form also, where there is some column, you take x1 of that column, there is another column, you take x2 of that column, you combine them, and you will get the result, which is b. So you can consider here. So again, this column you can consider them as a vector and draw here. So this blue one is column 1, and this column 2 is shown by green one. So from the row picture we saw that our solution is x1 equal to 1 and x2 equal to 2. This was our solution. So let's plug here and see what is the picture. So if you take column 2, put on top of column 1, take twice of that, then the result of this and this. So basically we take the column 1, put column 2 here, so ultimately we reach a point here which is 0, 3, which is nothing but this red line, which is nothing but the right hand side. So you can see right now, like how can we see the system of linear equation into in a column picture, like we are taking column 1, column 2, and we got ultimately we got x1 and x2, some x1 and some x2, which will leads us to this column, which is B. That means this red one. So this is the column picture. So let us ask some questions like can you imagine all the combination of column 1 and column 2? Suppose this is column 1, this is column 2. So if you took only this combination, that is 1 times of column 1 and 2 times of column 2, it gave you this vector. If you take like thousands of random combinations, what do you think what will be the result? So you will realize that you can, the resulting vector all the time will be something like this depend on the various selection of x1 x2. So basically you can complete the entire R2 plane. You can generate the entire R2 plane with the linear combination of column 1 and column 2. So in that way you have to think. So yes, let's keep all these things in our mind. Let's see what is happening, what how can we see the problem. So that's the goal of the lecture. So now let us jump into the I hope this is clear how we visualize things as in column way and how we visualize them in row picture. So let's take three equations with three unknowns. So this is the three equations. Again, you can write them in matrix form. There is a B right hand side, and row picture will be some. And see, in two dimension the rows when we are drawing. So the each equation was representing a line. But if three unknowns, three equations, each row will represent a plane this time because we have added one more dimension. So in that earlier case here the intersection of lines were the solution. So in case of three equations and three unknowns, the intersection of plane will be our solution. And obviously it is quite difficult to imagine here. You can imagine first equation represent some plane, then you have to draw another plane on top of that and another third plane, and the intersection of all those three planes will be your final solution where all three equations are satisfied. So this will be the row picture for three unknown three equations, and the column picture will be something like this. Again you have three columns, column 1, column 2, column 3, and you can see that if you by intuitively you can see that if you put x1 equal to 0 and x2 equal to 0 and x3 equal to 1, your left hand side will become same as right hand side. Those obvious solution is x1 equal to 0, x2 equal to 0, x3 equal to 1. So B is nothing but the column of 3 for x1 x2 equal to 0 and x3 equal to 1. So you can see that this will be the solution in terms of column space, column picture, not sorry, a column picture. This will be the column picture. So like we observed here for 2D space, you can observe here for 3D space. So let's think about it deeply. So can we solve Ax equal to B for every B? So you have to keep these questions in your mind. However, we will answer them very clearly in coming lectures, not now. So do the linear combination of the columns fill the entire 3D space? When it will happen? So for the above matrix, that is this matrix A, it is the answer is yes. We can fill the entire space with the linear combination of all these three columns, and A should be a non-singular matrix for that. Again, you don't worry about non-singular or singular anything. This is, I am just giving you some ideas. You don't have to worry. We will discuss everything in the coming lectures. So just I'm saying that these are the things that we need to think about it. So let us take an example. If all columns lie in the same plane, then their combination will also lie in the same plane. In that case, 3D space cannot be filled. So in that case, A will be singular, like A will not be invertible. Again, don't worry about this thing, we'll discuss. So you can imagine, right, if you take a vector in 2D plane, and again you take a vector in here in 2D plane and again another vector in the same plane, obviously the result cannot go to result will always be in that plane only. So we cannot leave that 2D plane if with only two vectors if they are in the same plane. So if to result cannot go out of that plane, it is quite intuitive, right? So these are the things. Yes. So let us see the matrix picture. So it's nothing but representing the system of linear equation in Ax equal to B form. That is this one. Then B. Now you can consider this Ax as nothing but this is the A matrix. This is X. You can consider it as a uh, that you take this column, multiply by 1 and take this column and multiply it by 2. So it is nothing. Ax is the linear combination of the columns of A. So you take the column of A, multiply by 1, then another column of A, then multiply it by 2. So it is nothing but a linear combination of columns of A. You can think in that way. So again these are just some ideas we need to focus on. So let's come to the general form of a system of a linear equation. So this is the general form of system of linear equation. We have m equations and there are n unknowns, so we can represent in this form. So where aij belongs to r is a real number and bi also real number, and x1 to xn are the unknowns of the systems. So every n tuple that satisfy equation 1 is the solution of the linear equation system. So every tuple of collection, you can say x1 to xn, that satisfy this set of equations will be the solution of this linear equation system. So in general, for real valued system of linear equations, we obtain either there are three possibilities: either there is no solution, exactly one solution, or infinitely many solutions. We'll look into it. Well, I'll explain this line. So consider the case where you might have heard linear regression, right? So linear regression is nothing but it solves a version of these equations, that is I have showed collectively as equation 1. Linear regression is nothing but a version to solve this set of linear equations when there is no solution at all, where we cannot solve the system of linear equations. So we cannot solve them exactly, so we solve them approximately, and that is nothing but linear regression. So this thing I will explain in geometric interpretation. A real valued system of linear equations, we obtain either no solution, exactly one solution, or infinitely many solution. In our earlier case, whatever examples we have showed, we were obtaining one solution. So here let us look at the geometric interpretation summary. So in a system of linear equation with two variables x1 and x2, we observed that the solution set is the intersection of the lines represented by the equations. Recall the row picture. That's what we have done. So there are three possibilities. So suppose the intersection can be a line if the linear equation describes the same line. Suppose we have two linear equation, y equal to x and 2y equal to 2x. So these are the two lines. So that means these are the intersection will itself with the same line. So that means we have infinitely many points lying on this line. So we will be having infinitely many solutions. There is not even there is no one point overlap. There is an entire line is overlapping. So that's what I meant when I wrote here. A general system of real valued equation can have infinitely many solutions. So this is the case where you can have infinitely many solution, and again exactly one solution, like our normal case where we have line 1, line 2, and their intersection is the solution. So this is exactly one solution. And there might be the case where there is no solution at all. This is the empty. When the lines are parallel, you can consider this is the one line, this is another line, so they don't meet at all. They meet at infinite. So that is no solution. So these are three possibilities: infinitely many solutions, exactly one solution, and no solution. Again, at the after few lectures I will give you a straight set of rules to find all these things. For now I am just letting you know that what are the possibilities, what are the things we need to take care of. Yes. So similarly, for the three variables, each linear equation determines a plane. Okay, let me come here. Real valued system. Yes. So here I mentioned, like, for 2D case, for two unknowns, the intersection can be a line, a point, or empty space. And when you move to the 3D space, the intersection could be the intersection of these planes could be a plane, a line, a point, or a empty when the planes have no common solution. So in 2D case, the intersection could be a line, point, or empty. In case of 3D, since we have added one more dimension, the intersection could be a plane, a line, a point, or empty. So these are three interpretation, three possible solutions. So let's create some compact notations, and we will be following this notation for the entire course. So again, this system of linear equations can we can write this in compact form, that is ax equal to b form. So we can write something like column 1 into x1 plus column 2 into x2, something like that, equal to b1. And you can write this entire thing into a matrix. We call it as a coefficient matrix, then the unknowns, and then the right hand side. So it is of ax equal to b form. So this is the compact notation, and in next lecture we will talk about matrices and define computation on that and some rules. And after that we will return back to solving the system of linear equations, and I will give you a set of steps to compute the same. So that's the end of the lecture. I will meet you in the next lecture. Thank you.